Hi again, I'm Frankie, and this is video 2 of a 4-part series about active learning. As a reminder, we introduced active learning in the previous video, so if you're interested in getting started, start there. This video is more about the algorithm components that constitute an active learning algorithm. This talk will go over the components of the data and the annotator, the learning model, the query policy, and an optimal stopping condition, and all of these parts form together an active learning algorithm. Visually, let's step through an active learning algorithm. It is an iterative algorithm, as we reviewed from the previous talk, and it's like a while loop, so it's going to iterate and then enter into this cycle. It begins with an initial data set. So your data, as a reminder, is capital D sub L, where L is labeled, and we're going to use 0, that, comma, and then I as your iteration. So for the initial, your I is equal to 0, and the data constitutes of some input X and output Y. You're then going to give that data to a learning model, and that learning model will train itself with that data. So you feed it the training pairs X and Y to get some function approximation F hat. That is your model. You then pass that model over to a query policy, which we will notate as G, and the query policy will then give you the next location to sample. In this case, the location to sample is your input X, for the next iteration 1. So you give that location request over to an annotator, which will then, the true function will generate the output, so the target output Y associated with your request input. You then feed that training pair back into your data, and you append it to your big data. And so I've changed all of the iteration, the I subscript, over to signify that this generalizes beyond just the first iteration. This goes until you hit some optimal stopping condition, which will signify with H. And it usually takes in the function approximator to decide whether the while loop should stop. So in a more clean way, these are the names of the algorithm components that we're going to step through in more detail for the rest of this talk. The data, what we start with. As a reminder from the previous video, all of the data is a union set of some labeled data and some unlabeled data. Labeled is L, unlabeled is U. And the data is composed of training pairs of input X and output Y, where you can look at it iteration by iteration. Let's say you were to sample 1 point every iteration, these subscripts would be the training pair sampled at that iteration. And we'll assume that the X and Y are in the real domain, numerically. That input and output pair was generated by some true function F that maps X, your input, to some output Y. Now remember, we only have access to the labeled data. And so the labeled data set, which is your training data set, looks like so. But we assume that we have access to the unlabeled data, which we'll call big D sub U. And at every single iteration where we try and sample, so the query policy, it tells you where to sample. Your annotator is then what looks into that unlabeled data set and gives the output assignment to the request. It is annotated with some true function, F. So that new data point that we just got, little d I plus 1, that training pair looks like X I plus 1 and then comma Y I plus 1. The annotator can come in different forms. So an annotator is anything that can assign a label, and the different ways the label can be assigned is through some user. Let's use an airplane as an example, and you are trying to assign, let's say, the input space could be like anywhere on the airplane, and then your output could be what is the airflow at that location on the airplane. A user, maybe not a very good annotator, but can say, well, what I observe on the airplane is that at this point, the airflow is going like so. A simulation could also act as an annotator. Here is some CFD simulation where there is airflow passing through the wings of an airplane. And so you can go into that simulation and probe somewhere on that airplane and ask the simulation, what is the airflow at that point? You could also ask the physical system, let's say you actually have an airplane built and that there is some sensor on that airplane that you're interested in sampling. Well, then your airplane sensor could be the annotator as well. The next part of an active learning algorithm is the learner. The learner is trained by the labeled data set, so that is the input signal, and it generates some f-hat, a model. That model learns a mapping from the labeled input, XL, to the target output, YL. That model can then generate a prediction of the target output across the unlabeled data. So not only did it learn the labeled data mapping, but then it can predict the mapping from XU to YU. The learning model does not have to be the same structure as the true function. So we saw the true function in the annotator, and it can be a variety of forms. Well, your learner can also be a variety of forms, and they do not have to mirror the true function f. The learner, as we'll talk about in the next video, can take on many different forms, and they definitely, while you would want it to be as close to the true function as possible, there are ways of avoiding that. So different flavors of the learner. You can have learners that are universal approximators that cap the error across your entire data, where the error is between the function approximator, your learner, and the true function. And you just want to make sure that as a universal approximator, that your model is expressive enough that it is able to approximate your true function well enough that it's always below some threshold error. That is a data agnostic approach. If you were to lean into your domain, then you could possibly use your data to inform what kind of form and function your function approximator takes. An example of that could be that you know the mathematical expression of your true function, and all you have to do is estimate the parameters, the coefficients that fit inside that mathematical expression. So in a way, you are very much using your domain knowledge and then refining and learning the parameters based off of the training data set. But because I want to be as agnostic as possible and as helpful to you out there, I'm not going to assume very much about the domain information at all. We are going to talk about universal approximators in this video series. The next component we want to talk about is the query policy. The query policy tells you how to sample. It considers the learn model F. The query policy is called G. It takes in f-hat, and it generates the location of the sample that you want to sample next at iteration i+1. The query policy can also take a couple of flavors. In general, the query policy is some optimization problem where you take in some learn model and the argument that you want to optimize over is over your input domain X. Now there's exploration and exploitation. Exploration, what you'll notice is the G is now replaced with I, because exploration optimizes information, which we'll signify with I, over unvisited samples, so that argument is over DU. On the other hand, exploitation is optimizing some objective, and we'll call that J, borrowed from control theory or dynamic programming. And you want to optimize over the arguments across all of the inputs, across all the data. So you see, there are two different ways that you can sample. You can sample in a way that optimizes for information, or you can sample in a way that optimizes some objective function. So for example, I'm going to use my arm as an example. Let's say that I'm a robot and I want to characterize the motion of my arm based off of the joint angles are my input space, and my output space is where my end effector or my hand is. And so if I were to just explore the space, I would try a bunch of variations of my arm. For exploitation, let's say the objective function J is just that I want my hand to be as high as possible. That's the objective. Well then, I wouldn't really want to explore all of these different joint angles that don't put my arm up high. I will go directly into the arguments, the joint angles, that puts my arm as high as possible. So that's the difference between exploration and exploitation. And for this video series, we are specifically going to optimize for exploration or information. The last component of active learning is called an optimal stopping condition. It's a condition, H, that considers the learned model, F hat, and indicates when to stop sampling. And so some examples of this, the very simplest example is that, let's say you have some budget for how many samples you can take. And so once you have met that budget, then you have to stop sampling. Mathematically, the criteria H could be that I is below some kind of maximum iteration. Let's talk about something a little bit more nuanced. Let's say that you can actually calculate the error associated with your learning model. Well then, your stopping condition could be that you want to make sure that the error across all of your predictions is below some threshold. So let's say error of F hat is below some threshold. Specifically, that threshold could be measurement noise, which makes sense because if you have noise in your data, then the best you can do is replicate or reconstruct your data up until measurement noise. Let's talk about another way to stop. So if you have access to your learner and it can generate some kind of uncertainty criteria, then you can use that criteria as a stopping condition if it's below some threshold. So let's say some sigma of F, where sigma is uncertainty, has to fall below some threshold. And more specifically, you could also, again, use measurement noise as that threshold, where sigma has to be below some sigma measured. As a reminder, here is the flow diagram that represents an active learning framework where we talked about data, how to learn, how to query, and how to annotate, and how to stop. I hope you learned something from this second video in the active learning video series. Stick around for the third video if you want to talk about learners and query policies some more. See ya!